This is Coda, my robotic quadruped that I've been working on for the past few months. What makes robotic dogs expensive are actuators, but I built Coda for less than £100 using these. I've always wanted a robot dog, but they can be kind of expensive. So I figured, I'm an engineer, why not just make one? So step one was to go into YouTube and to do some research. So I watched a bunch of people's videos, and there was this common theme about how they work.
My own quasi-direct drive actuator using a brushless motor, an FOC controller,
12 Eagle Power LA8308 motors,
refining the QDD100 quasi-direct drive actuator.
This is a brushless DC motor. It's got a really high torque density, it's sometimes called a pancake motor, and it's really good as a robotic actuator. The really cool thing is this FOC controller. Basically, it allows you to get the most out of your brushless DC motor. The main problem is that these motors are a couple £100, and the controllers aren't much less. So trying to stack this for all the actuators that you need for a robot dog, like 12, gets really expensive really quickly. But if you want something really cheap, you can use these. These are just regular DC servos that use PWM to set the servo position. They're really cheap and they're really easy to use, and I think I can make a robot dog out of them. With the robot, we're controlling the feet. There are 4 feet, and each of these need to move in the X, the Y, and the Z directions. So 3 different axes, so we need 3 motors. So we have these servo motors that I just bought from Amazon. We can use one for the X, the Y, and the Z. So this is the servo motor. There are 4 mounting holes, there's the output shaft that we're going to fit a horn onto, and then we have the cables. So 3 cables, the power, the ground, and the signal. So we have these 3 servos now, but how do we actually use them in some kind of leg to make this foot move in all the directions and paths that we want? That's where we need to design some kind of linkage. So I've started here with a fairly standard leg shape with a hip, a thigh, and a calf, and I put a servo controlling each one of them. Now by moving them all in the right way, the foot can move in all 3 axes. The main downside with this configuration though is that the calf servo is all the way out here, so it just acts as a torque arm that will burn out the thigh servo. So we can rearrange things a little bit and use a linkage to move the calf servo up to the top with the thigh servo, while having all the same mobility as before. But now this servo becomes a torque arm for the hip servo, so we can change the linkage again to move the calf servo right next to the thigh servo. A bit complicated, but I think it looks cool. So that linkage is all well and good in CAD, but I think I need something physical to actually see how this mechanism works. So let's make something. So I've just made this leg linkage model to see how all the members react when the foot moves. I'm pretty happy with it. There aren't obvious places where it buckles or breaks. I can't quite visualize how the actual servos will need to move, so let me just... So I've just changed the color of these 2 members, which will have the servos attached. And I'm quite happy with the range of motion going on there. You know, they both move at similar speeds and they don't really jump around a lot. So yeah, I think we'll go with this. So yeah, this is Taser. He's an engineer that I've been watching for a while on YouTube. He makes some really great videos. He's working on a robot dog project of his own right now. So I was on YouTube last night and I saw this. And I thought, yeah, that looks a whole lot like my linkage. So to be fair to him, I don't want to plagiarize his work or anything, so I think I'm going to go back to the drawing board and design some alternative leg linkage. Okay, so back to this linkage. I like how these 2 servos are adjacent to each other, so we can take it apart and do some rearranging. I got this idea from a video I saw of an Indian shopping account on TikTok of a drawing robot. But this is just a 4-bar linkage, and we have the same leg parameters. We have the 2 servos being next to each other at the top and a single foot position. And we can move this foot in 2D space using just the angle of these 2 servos. The downside is that we can get some buckling like this happening. so we're going to have to limit the position that these thighs can be in. But this is why we do these prototypes in the first place. Cool, let's get this working with some servos. So now this is all together, we can properly test this mechanism with our servo motors. I'm using these 3 potentiometers to control the angle of each servo, and the linkage will just carry that movement down to the foot. So right now I can control the hip servo, the front servo, and I can move the rear servo, and you can see how the foot moves. But this way of controlling the foot is rubbish. You know, if I wanted to move the foot directly up and down, for instance, I would have to move these 2 servos in steps sequentially, which would take ages. So imagine trying to move the foot in a more complex path, for example taking a step. It just wouldn't work. This method of controlling the foot position is called forward kinematics, where we control the servo angles and the foot just moves wherever the linkage carries it. What we want to be able to do is to define the foot position and for the servo angles to be worked out automatically. And this is called inverse kinematics. Can be solved a bunch of different ways, but since we have 3 motors and 3 degrees of freedom, the foot, X, the Y and the Z position, we can solve it with just a bit of trig. Let's look at the leg side on. We have 3 main points, the hip, the knee and the foot. These points are defined relative to this blue dot, which is just the centre of the robot. We define the foot Y and Z positions, and we're trying to solve for the hip angle and this length B, which is basically the extension of the leg. We can find B by splitting the shape into 2 triangles and doing a bit of Pythagoras. Then we can find the hip angle by splitting it into 2 and doing a bit of trigonometry. Nice. Looking at the front now, we define the foot X position, and we can bring in this extension B from the side view. There are 2 thighs and 2 calves, and since their lengths are constant, we can draw these circles. And where these circles intersect are where the joint can be. Now these points move when the foot moves, so we just pick the points we want, and then since we know the positions of these points and these points, we can calculate these angles for the 2 servos. And combining all this together gives us a single function that takes in the foot coordinates and outputs the servo angles. Awesome. Okay, so I've programmed that inverse kinematics routine in, so what I'm going to do now is use these 3 potentiometers from before to set the foot X, Y and Z coordinates. So we can set the X position, we can do the same with the Y, and we can also, which I think is the coolest bit, move the foot Z position, which requires all 3 servos moving in tandem to set the foot position. So we've made a bunch of progress here. We've selected the motors, we've designed a leg and we've tested it, we've solved and implemented the inverse kinematics, so really, we're just about ready to start designing the robot. Okay, fine, I just really want to start designing this robot. It's cat time, baby. Right, now that code is all designed, it's time to put it together. Some insane mechanical design means that she can be assembled in just 15 seconds. Don't believe me? Ladies and gentlemen, I'm pleased to introduce you to Coda. She weighs 2.8 kilograms, which is probably due to these oversized bearings I'm using. So yeah, this is Coda. I'm really happy with how she's come out. She's a little heavier than I anticipated, but I've done some rough calcs and we're well within the ratings for the motors. This carry handle is really useful. So the next challenge is how to actually drive all of these servos at the same time. I initially bought this, which is a servo breakout. It's really good, but it's only rated for 6 volts, so not really enough for what we need. And these terminals to carry the power are really small. So with a bit of research, I found this. This is a Servo 2040 board, and it's rated for 11 volts with 10 amps of continuous current draw, which is great for what we need. The really cool thing about it though, is it has this Raspberry Pi 2040 chip on it, which means that we can run MicroPython on it. So it's basically a microcontroller and a servo driver at the same time. Right, let's wire this all together and see what we can do. So yeah, the main downside of this board are these really small power terminals, and since we can draw up to 10 amps, which is a lot of current, with really small wires that equals a lot of heat. So I'm going to try and bulk up these wires as much as I can and try and be cautious about how much current we're drawing. The next step is to get the feet moving along some defined path, and to do that we need to control how the servos move. Now the problem is that servos just move to their target position as fast as they can, but with proper robotic actuators, you can define some specific motion profiles, like a trapezoidal profile. The actuator would then use multiple control loops stacked on top of one another to execute that profile, but with servos we just don't have that ability. The best thing we can do is to break the profile into steps, so the servo moves from one step to another, simulating the path. This is okay, but it's certainly not smooth. We can increase the number of steps to smooth out the profile, but one issue is that once the servo gets a new target, there's a big torque spike and a current spike. This is bad because if all the servos are doing this, and there are lots of spikes, you'll have really high current draw, the motors will get hot and wear quickly, you're going to drain your battery, not really a good idea. Servos also have a maximum control frequency, so there's a hard limit to how small these steps can be anyway. So we've got to balance the smoothness with this current issue, which I'm going to do on vibes alone. Okay, so now I've got this working so that the legs move. Coda, stop. The legs are moving back and forth. But this poses the question, how do I make it walk? The mechanics of walking is mainly made out of two things. You have the foot trajectory, which is just the path that the foot follows when it takes a step. And then you have the gait pattern, which is just the order of which foot moves when. Starting with step trajectory, to do some research, I needed to find a mammal with about the same level of intelligence as a dog. Here's one I made earlier. You can see that there are two clear phases to the step. You have the swing phase, where the actual step is taken, and the stance phase, where the foot is in contact with the ground, pushing against it. Now there are a bunch of different step shapes, but I've chosen to go with the cycloidal step trajectory with the corners rounded for a nice natural step shape. Moving on to gait now, if we look at our test subject, you can see that as one foot is in the air, the other foot is on the ground, and then they alternate. And this is all well and good for 2 legs, but how does it work for 4? Here you can see that there's actually a very similar thing going on. The pattern is that alternate limbs match, so while that 2 in the limbs are in the swing phase, the other 2 are in the stance phase. Now this is actually called the trot gait, where diagonally opposite limbs move together, but there are a bunch of different gait options. You have the
crawl
gait, where only one leg is moving at a time, and then you have the gallop gait for some really dynamic movement. We're going to start with the crawl gait, because it's the easiest to implement, and because it should be the most stable of the gait patterns that we've discussed. I programmed the cycloidal step trajectory in, and that's running quite smoothly on the robot. The code works by breaking the path into steps and working out the inverse kinematics for each one. It then just runs through each of those steps one by one to execute the path. You'll notice that there are more positions in the stance phase, which is how we make it slower than the swing phase. Getting this to work on multiple legs is actually really easy. The inverse kinematics is pretty much all the same, so we just apply the path to each leg. The only thing we have to sort out is their timing, otherwise you get this. The timing all comes from the gait. We set the starting positions of each foot and the duration of the swing and stance phases, and with just those 2 parameters, we can generate any gait pattern that we want. So after a few code mishaps, here's the crawl gait implemented on the leg. I'm happy that it's doing the right thing, so let's try it out. Okay, so Coda is walking, but it's very unstable. And to look at the reason why, we need to look at the centre of gravity. Coda is designed so that when one foot is off the ground, the centre of gravity is within the support triangle. But in reality, the dynamics mean that the centre of gravity moves around, leading to this instability. Really, we would want to be able to move the robot while walking to move the centre of gravity, which would be a good idea for the next version, but I think the easiest fix is just to lean into these dynamics and use the trot gait instead. I think it's time to take Coda for a walk. So there's one more thing I want to unlock with this robot, and that's orientation control. Currently we can move the legs, but we can't really control where the torso lies. So really, Coda can't dance. To show the maths on this a little, we start by defining 4 feet stationary to the ground and this torso centre. We stick some axes on the torso and 1 on each hip, and these all react when we change the torso pose, but the feet stay still. Then all we do is find the coordinates from the hips to the feet using the hip axes, plug that into the inverse kinematics, and then we have servo angles to achieve the pose we want. Let's see it in action. Okay, I think I'm going to call it there. I'm really happy with how Coda has come along, and I'm one step closer to having that robot dog I always wanted. And I didn't break the bank doing it. Coda came in just shy of £100 for all the servos, 3D printing materials, fixings, and electronics. Of course, as an engineer, I'm never 100% satisfied with my designs, and there's loads of things I want to fix and upgrade. To mention a few, you got these fixings which fall out constantly and are a pain to refit. I want to change the foot material so it doesn't slip as much. I want to have some servo zeroing during startup. There's a bunch of code optimizations I want to do. And the big one is getting rid of this lead and making Coda a battery-powered remote control quadruped. Plus a whole list of other upgrades. So stay tuned for the Coda V2 video that will come out sometime in the future. This project has been my life for the last few months, so truly, thank you for watching. But before I go, there's one little upgrade that I think Coda has earned.